We'll get started. I have 2 after the hour. Welcome everybody to the Near Surface Geophysics Virtual Section Reception and Awards Recognition. This is the first one of these we've done, at least for some time, before the AGU fall meeting. I'm Burke Minsley. I'm the current section president of the Near Surface Geophysics section. Just a quick agenda for today's meeting. Pretty simple. I'll talk for 15 or 20 minutes on the state of the section, some highlights for the fall meeting starting next week for those of you who will be in attendance. And we'll talk about people who received awards in the past year. Then at 12:20, these are Eastern times in the US, we'll have an invited talk by Sebastian Ullman, our Near Surface Geophysics Early Career Achievement Awardee. If anybody has questions during the presentation, feel free to put them in the chat. Hopefully anybody on the executive committee can chime in and answer those, or I can try and answer them later. If we have time before Sebastian's talk, we can take a few questions in person if you have them. So first off, I want to recognize that this was an election year within AGU. Hopefully most of you voted and selected your candidates in the Near Surface Geophysics section and across AGU. On the left-hand side, you can see the transition to the new Near Surface Geophysics leadership starting in January of 2023. Chi Zhang will take over as president. Jonathan Aho Franklin as president-elect. I will become past president, and we'll have Sebastian Ullman, our new secretary. At the same time, I want to give a big thanks to our outgoing past president, Xavi Comas, who's now acted as 6 years as president-elect, president, and past president. So thank you for all of your time, and also Leah Cortland, who's been our secretary for the past 2 years. And I say thank you to you both and not goodbye, because I know that you'll both be still involved with the section in the coming years. This is what the rest of the Near Surface Geophysics Executive Committee looks like. You can see we have a number of different roles. This is our membership in 2022, so please reach out and thank the folks who are involved here. I know we always have people coming and going on this committee, so if you are interested in joining the committee in 2023, please reach out to one of us and let us know, and we'll gladly help to find you a spot in this group. In addition to serving within the committee, AGU is always seeking volunteers in various aspects. If you look on this web link on the left-hand side of the slide, you can go sign up for various AGU volunteer activities that could be at the union or section levels. And of course, AGU always appreciates your support, both in your time and with your dollars. So you can donate to AGU in various ways using the link here below. One of those ways that you can donate to AGU is directly to the Near Surface Geophysics section. Your donations all come to the NS section. And if we receive donations of $50 or more from at least 5% of our primary members, that's only about 30 people from our section that has a little over 600 primary members, AGU gives us an additional $1,000 to support various student and early career and other activities in our section. So please consider that in a donation either this year or next year. And I also want to make a big thanks to our corporate sponsors. This year, we have both GSSI and SkyTem helping to support the Near Surface Geophysics section. GSSI has long supported the student research grant that you'll hear a bit more about later. And SkyTem has provided contributions that help the section do things at the fall meeting again, largely for our student and early career members. So thank you to both of these companies for their help. And if you're a company out there looking to support the Near Surface Geophysics section, please reach out to one of us on the executive committee. Okay, so next up, we're going to turn our attention to the fall meeting. Hopefully, many of you will be attending the fall meeting and we'll be able to catch up there in person. Just give you a brief rundown of some of the things happening at the fall meeting, especially in our section. A few numbers about registration and what's happening next week. These stats are now a week or two old. There were a total of over 18,000 people registered. with a little over 3,000 online and 15,000 in person. I've heard that in-person number is now over 16,000, which is a pretty good tick up from what we had last year. So not quite to where we were pre-COVID years, but quite a few people attending in person. You can see where you'll be able to get your badge at the McCormick Center and also the Sheraton Hotel. You should have received an email from AGU about safe access verification. Make sure you complete this before you get on site to just help streamline your ability to get through the registration quickly. And here you can see the top 5 countries outside the US where people are coming to AGU from Canada, UK, Germany, Korea, and India. So now turning to the near surface geophysics section at the fall meeting, we had over 200 abstracts submitted to various NS sessions. You can see there's a lot going on during the week. So you've got the columns here are days of the week. Each row is a different time of day and presentation type. So the light blue are posters, both in the morning and the afternoon. What's a little different this year is that we have free in-person poster, online poster discussion. So that's at 8 to 9 in the morning. These are Central US times, and 1:45 to 2:45 in the afternoon. Then we have the typical in-person posters in the poster hall, once in the morning, once in the afternoon, and oral sessions, again, both in the morning and the afternoon, as well as a town hall on Wednesday at 12:45. This is discussing the workshops held over the past year, talking about the idea of supporting a future near-surface geophysics center in the community. So you can see there's a lot going on in the section throughout the week, something happening every day and lots of different disciplines. So hopefully you'll find lots of good science here. I'll make a plug for the OSPA. So these are the Outstanding Student Paper Awards. This year, there are 39 students in the section participating in the OSPA. And we want to have 3 people judging each of those presentations. So that means we have 117 or so judging spots that we need to fill. So please pull out your phone, scan the QR code on the left of this slide. That will take you to the judging site with the list of all of near surface geophysics student presentations that you can help to judge. During the meeting, we're going to also have additional QR codes that can bring you directly to sign up pages for presentations, to try and make the process as easy as possible, to provide feedback to these folks who are presenting, some of them for their first time at the fall meeting. So thank you in advance for signing up for those. Other events happening within the section and beyond at AGU. On Monday, we have the Hydrology, Global Environmental Change, and Near Surface Geophysics Early Career and Student Trivia Night, a networking event. Tickets were required for this. If you're a student early career member who's really interested and keen to go and weren't able to get a ticket, let me know and we'll see what we can do, but I can't promise anything. On Tuesday evening, there's the near surface reception, sort of the in-person version of what we're doing right now, as well as a larger neighborhood gathering. This is at the Marriott Marquis and the Hyatt Regency, Tuesday, 6:30 to 8. Tickets were also required for this event. Hopefully that wasn't a barrier for too many of you. But again, if that was a big challenge and you're still interested in going and can't, let me know and we'll see what we can do. Beyond the near surface geophysics section, there's a lot of other interesting things happening sponsored by AGU during the week. There's an Adler Planetarium night on Wednesday. The first 2,000 people to visit at the on-site registration desk can receive tickets for that. On Thursday night is the night at the museums. Sign up for this starts at 2 o'clock on the 13th. So I assume these are going to be pretty popular items. So if you're interested in those, try to get tickets for those events. And you can find tons of other things like goat yoga and everything else on the AGU website that's happening during the fall meeting. If you're not interested in going to the night at the museums on Thursday, we have an alternate event for you, the long-standing Near Surface Geophysics, Hydrogeophysics Technical Committee Joint Social. We're hosting this this year at Kroll's. You can see the location on the map here. It's about a 20-minute walk from the convention center. This is going to be on Thursday from 7 to 9 o'clock. We have some reserved space in a room here, but drinks and food are going to all be on your own to order and do what you like. So love to see many of you there as well. Okay, and so lastly, I want to move on and recognize people who received various awards and honors during 2022. First up are the student travel grants. So student travel grants for the fall meeting help to assist students with cost associated with attending the meeting in person or virtually. In-person attendees receive grants in the amount of $1,000 to cover fall meeting expenses. Virtual attendees, that's split in half, with $500 going towards general educational expenses. So this year we had 2 student travel grants awarded: the Sheikh Nassif Ahmed with a presentation ground roll attenuation of seismic data through the model-based inversion, a synthetic study, and Diodan Jean-Jacques for his presentation, understanding the subsurface of Garner Run and Bear Meadows through the eyes of ground penetrating radar. So congrats to you both, and hopefully you're able to use those funds to help support your attendance at the fall meeting in person or virtually. Next up is the David Miller Young Scientist Scholarship Fund. This is relatively new in AGU, I believe, and it's for undergraduate and graduate students in geoenvironmental sciences and engineering. It's a $1,500 scholarship for students who exhibit an interest in academic potential in fields related to earth science. There's one winner selected each year, and we're very pleased to say that this year that awardee went to Lal Mahmood, a member of the Near Surface Geophysics section. His project is titled Application of Self-Potential and Electrical Resistivity Tomography Geophysical Methods for Aquifer Characterization and River Groundwater Interaction Monitoring at Shell Mound, Mississippi. So congratulations, Lal. Last year, I told you about signing up for judging OSPA presentations this year. We awarded 3 OSPA student paper awards from the fall meeting in 2021. Those went to Martina Tenti from Ca' Foscari University of Venice for her presentation post-LGM grounding of line positions of the Drygalski Paleo Ice Stream Trough Basin in the Western Ross Sea and Antarctica. Adrian White at Bristol University, geophysical mapping of badger tunnels and levees. And Harriet Zoe Yin from Scripps, with a presentation, real-time building, monitoring for rapid response to earthquakes. So congratulations to last year's OSPA award winners. This GSSI student grant was established through the generosity of GSSI to support near-surface geophysics section student scientists who conduct field geophysical research using GPR and electromagnetic methods. This research grant comes with a cash award as well as an opportunity to rent equipment from GSSI as part of their research. This year's award went to Bruno Bellotti from the University of Idaho. So congratulations to Bruno. The Near Surface Geophysics Early Career Achievement Award was established in 2020 and is given annually and recognizes significant contribution to the field of near surface geophysics by an early career researcher. This award this year went to Sebastian Ullman from the Lawrence Berkeley National Laboratory, as I mentioned earlier, also our new section secretary. And Sebastian, after I'm done here, will be giving an invited talk afterwards on the use of geophysics in hazard studies. Congratulations, Sebastian. The Edward A. Flinn III Award this is not a near surface geophysics section award. This is a AGU union award. It's given annually to mid-career or senior scientists individually in a small group who personify AGU's motto of unselfish cooperation and research through their facilitation, coordination, and implementing activities. The award is for unsung heroes who provide ideas, motivation, and labors of love that build and maintain the infrastructure without which our science could not flourish. This year, the award went to a group of near surface geophysics affiliates, Martin Briggs, Kian Dawson, Carol Johnson, John Lane, and John Williams, who, if you know these folks, certainly live up to to the motto and intent of this award. So congratulations to you all. And finally, we're very happy to recognize Estela Hatequana, who was elected a Union Fellow through the Near Surface Geophysics section this year. The AGU Fellows have earned this recognition because of remarkable innovation and sustained scientific impact. Fellow embodies AGU's values by fostering equity, integrity, diversity, and open science, by mentoring public engagement, and through their communications. And Estela certainly embodies all of those great qualities. The recipients join a prestigious group. There is only 0.1% of members who selected to receive this honor each year. And AGU Fellows are global leaders and experts who propel our understanding of geosciences. Their research pushes our boundaries of knowledge to create a healthy planet and beyond, and are inspirations to us all. We're grateful for your contributions, hard work, and sacrifice, and great congratulations to you, Estela. And so that's it for this year's awards. I would encourage you all to consider submitting nominations for awards in 2023, whether that's for the Near Surface Geophysics Early Career Award, for fellows, or other union medals and awards. The awards process for 2023 starts in January, so that's right around the corner. And we'll be able to celebrate these awards back in San Francisco, where the fall meeting will return in December of 2023. And so that's it for me. I'll hopefully see you next week in Chicago or next year in San Francisco. If there's any quick questions, I don't see anything in the chat. If anybody has a question, we can do that now while we let Sebastian set up for his presentation. Otherwise, Sebastian, go ahead and share your screen. Should be able to. And take it away whenever you're ready. Congrats again, Sebastian, and thanks for giving this presentation on Near Surface Geophysics, a tool for landslide early warning.
Yeah, thank you very much, Berg, and thank you very much again for all your kind words. So, you know, I thought since I'm giving this talk as the recipient of this year's Near Surface Geophysics Early Career Achievement Award, first I want to thank Andy Bindley for nominating me for this award. And, you know, you can see Andy here sitting in the field in between a lot of cows. But you know, Andy is always very helpful, and I'm very grateful for his support. And that's not only for this award, but also in general. So every time, you know, you need his help or you need his advice, he's always there. So for that, Andy, thank you very much. And I got this photo from one of his PhD students, Paul McLachlan. So you know, he had a lot of experience with Andy in the field, and I thought this picture or this photo was very nice. Him sitting very happy there and doing field work. So, you know, the award is called Early Career Achievement Award. And I think, you know, achievements are never done alone. So achievements are always coming out of field work, of teamwork. And this is something, you know, that Henry Ford already said, that working together is success. And for me, this started at the British Geological Survey, where, you know, I started as a research geophysicist within the Geophysical tomography team, which was headed by, or is still headed by John Chambers. I then went to Berkeley Lab, where I started working in a team of Baptiste Davlon, which we see here. And then, you know, you have the work that you do in the office, but as near surface geophysicists, we also go into the field a lot. So, you know, then you start working with all your teammates, and maybe sometimes you just sit somewhere in the Arctic in an Arctic oven and just look out for the driller who's not coming, and you're just sitting there and doing nothing. But it's not only that, it's also, you know, having friends in the community. Like here we see Florian Wagner, who spent some time at Berkeley with us. And, you know, we went a lot of hiking. Then in the middle we have Beto, who, you know, is kind of in my team since the last 12 years. So that's very good to have this support. And then, you know, if you look at the work that I've been doing at Berkeley Lab, I've been working at various big teams. Like on one hand, there's the watershed function SFA, But then there's also the NG Arctic project, where each of them has, you know, almost 100 people working on them. And then you start working not only with geophysicists, but with a lot of other people. And then at some point you see yourself sitting next to a modeler trying to explain them why, you know, the data that you acquired in your surface geophysics makes actually a lot of sense to be put into their models. So I think, you know, with all of that, what I just want to show is, you know, that I think teamwork is really what makes success. And that's, you know, comes back to what Henry Ford said there. So for this talk, I'm going to talk about landslides. And before I want to start, I want to give a very brief introduction on what landslides actually are. So a landslide very easily can be defined as the movement of a mass of rock or earth or debris down a slope. So really it's just the downhill movement of earth material due to gravity. And it can be caused by several factors. For instance, you can have earthquakes where you have co-seismic landslides, and we had an example of that just last week in Indonesia, where we had a big earthquake and then many landslides that caused a lot of fatalities. But these are the landslides that are very difficult to predict. So here, what we're going to talk about in the following are landslides that are more caused by heavy and prolonged rainfall, by erosion, and in the case of engineered structures, by poor building standards. So why do slopes fail? So there's a nice quote by Duncan and Wright that say, you know, except for the effects of water and clay soil, slope failures would be extremely rare. And from this, we already see that water is one of the major factors in triggering of landslides. And this is because water reduces the shear strength, but also raises shear stresses. So water is really important. And now with near surface geophysics, we're kind of lucky in that, you know, tracking water in the ground is something that we tend to be pretty good at. So near surface geophysics has a very good application for monitoring or assessing and characterizing landslides in particular. Then the other thing, if we look at this photo on the right here, which shows a landslide in Guatemala, shows that landslides can have multiple causes. So what we have here, on one hand, you know, all these buildings that are putting a load on these slopes, but then what we can also see in some of these areas here are broken water pipes. So we have some broken water pipes here, there, and there. And now, you know, it could have been that some of these water pipes have been leaking before this landslide happened and basically caused a rise in pore pressures in the ground, and that's why the slope may have failed. So what I want to show with this picture is just that landslides are often very complex, and characterizing and monitoring unstable slopes is often very difficult. So while I was at the British Geological Survey, we were mostly working on developing techniques to enable long-term geoelectrical monitoring of landslides. And these developments have been done at the Hollin Hill Landslide Observatory, which is, you know, located in North Yorkshire in England, and is basically sitting within rocks of the Lias group of the Lower Jurassic, where we have Whitby mudstone failing over the State sandstone formation. And with this geological setting is pretty, you know, representative for many landslides in the UK where you get these kind of things. The landslide itself is reasonably small, is only 140 meters kind of long, and has a slope gradient of only 12 degrees. This already shows you, you know, how weak and, well, how unstable the slope really is. So even though the slope gradient is only 12 degrees, you get quite significant movements. In this case, it's a slow-moving landslide, so movements are usually just less than a meter per year. And what we have are translational movements around here that are forming these slopes. And these movements then take away the support for the back of the slope, where we have rotational failures. So it's quite a complex system. Now, at this site, we have numerous monitoring instrumentations. There are you know, GPS markers, and there are tilt meters to record deformation. We have some moisture sensors and piezometers to get a good handle on groundwater conditions. And then outlined in red here is a 3D electrical resistivity tomography survey area that we used quite intensively here. But before I get to the ERT data, I want to show some of the characterization we did using P and S wave seismic refraction tomography. And we can see the P and S wave tomograms here, which basically show us on one hand, you know, where the regional groundwater table is. So that's this quick anomaly here, or high velocity anomaly. And here we see a perched groundwater table. Now, if we look at the S wave velocities, mostly what we're seeing is just an increase in velocity with depth. which represents the weathering conditions that we have at the site. Now, we did these surveys to get a better handle on the lithology at the site. But if you remember, I told you that mudstone is failing over sandstone, but we don't really see that in these tomograms at all. The expected lithological interface doesn't show up because we were expecting it somewhere around here. I mean, this is mainly because the seismic properties were just too similar. Then what we did is we calculated the Poisson's ratio from the P and S wave data, and now suddenly you can see this interface very nicely. So here, where we go from this wet material with high Poisson's ratio, which is basically saturated material, which is the would-be mudstone, we're getting into the material that is more dry, which is the state sandstone formation, which is drier because it has a higher permeability and hence, you know, the water drains. And so here we can now see the interface pretty easily. And we can not only see this in 2D, but we can also see this in 3 dimensions. And we use this then to constrain the ELT data. So we use the interface that we got, put it into the ELT inversion, and then we see the structure of the landslide very easily. We see the would-be mudstone as this conductive anomaly over the more resistive state sandstone formation, and we see also how these slopes are being formed. But often just reporting the resistivity or even the change in the electrical resistivity is of no use to anyone who isn't a geophysicist. So what we did here is we took samples from the would-be mudstone and the state sandstone formation, took them to the lab and established petrophysical relationships that link the resistivity to the moisture content. And so we have a Waxman-Smith model for both the mudstone and for the sandstone. And then if we apply that to the resistivity data, we can actually translate the resistivity into moisture content. And we see very detailed features then in this 3D moisture content model, where we even see small little features that, for instance, relate to lobe drainage, where we usually see just a little spring in the field that causes this somewhat higher moisture content anomaly. Now we monitored the site from 2009 or since 2009, because actually it's still monitoring. And what we see here now is basically the resistivity model underneath the aerial photograph. We see that the would-be mudstone formation is forming these lobes, and underneath that we have the state sandstone formation. Now what we're going to see now is the changes in moisture content over time. And what we see is basically some seasonal patterns. So we see some drainage in summer in this lower area of water that accumulates in winter in the would-be mudstone formation. So here we get this accumulation of water, which then in summer drains in between these two lobes down the slope. Now, 2010 and 2011 were pretty kind of standard years, so they were not exceptional in any way. But then 2012 was a very wet year, and we can see this already now. The summer was very, very wet. We see a lot of moisture, and then when we get into December, there was a lot of moisture, and that's also where we got failures. Now, what we did here is we actually accounted for electrode movements due to the landslide in the inversion. And then towards the end of it, we are still able, even though electrodes moved by more than 3 meters, we are still able to get these drainage patterns from the resistivity tomography. If we look at this in more detail, we can actually start to link the geophysics-derived moisture content that is shown on the top here with soil moisture measurements with measurements on a grounder table, and with measurements of soil deformation. So if we just look at the soil moisture content, we see this kind of seasonal pattern with lower values in summer, higher values in winter, and we can see this rise over the years. This relates pretty nicely to the measurements that we have from the piezometer, which also shows the seasonal pattern and this rise in the water table. And then we see from the deformation data that first we had no movements. At the end of 2012, we got a lot of movement. So if we put all this together, we can actually establish thresholds. And in this case, we could establish a threshold that shows that if we exceed 48% at this location of this slope, that's when we have to expect movements. And now this threshold actually proved valid in the last few years, that where every time we exceeded this threshold, we actually saw movements. So then when I moved to Berkeley, first I kept landslides somewhat behind, and I worked mostly on the SFA watershed and NG Arctic. But then I had an opportunity to continue developing some of this further. And here I started to focus on integrating geophysics with other techniques to develop, let's say, a more comprehensive approach that combines geophysics with environmental monitoring and hydrogeomechanical modeling to assess the safety of slopes in real time, but also try to predict it into the future. And this made use of these kind of advances that we did in geophysics, but also advances we have in machine learning, where now we can, in real time, assimilate data of various data streams. We can use machine learning to predict how things are going to change. And we're having now hydrological geomechanical models that are actually able to model things in relatively big domains in 3D. So, you know, assessing factor of safety is becoming more feasible. And because outside of my office, there was a bridge that was monitored using a ruler, I thought that perhaps focusing on the slopes at Berkeley Lab might be a good idea, just because there seemed to be a lack of technology. But also in general, the Berkeley Hills, as you can see here, and also the Oakland Hills, are actually very well known for, you know, landslide hazards. And in this map, you just see all the deep-seated landslides that have been active and are active right now. So clearly, it's an area of a high landslide hazard. So in 2021, Sylvain Fiolot then joined us at the lab, and he started to look into assessing the landslide hazard across Berkeley Lab using a hydrogeomechanical model, in this case, a Python-based model, which is called LambDA. So first, he looked at the sensitivity of this model to the input parameters. And what he found was that the model is most sensitive to the slope angle, the soil thickness, and the total cohesion. So now the slope angle is something that we can derive pretty easily from existing, you know, DEMs, for instance, from LiDAR data. But the other two parameters are more difficult. So for the soil thickness, we had a fairly good number of measurements or borehole measurements, but most of these, which are shown here in green, are related to buildings. So they're not necessarily at the right locations for us to use them to predict what the soil thickness is across the lab. So Sylvain went out with some 3D, some 3-component seismic sensors and measured the horizontal to vertical ratio at various locations, and he got, you know, various responses. In some cases, we see a peak that is at very high frequency, and in some cases, we see peaks that are very low frequency. Now, the change in this peak is related to a change in soil thickness. So where we have the peak at high frequencies, that's where we have thin soil, in the order of 1 meter or so. And where we have it at lower frequencies, that's where we have thicker soil in the order of 15 meters or so. And then the other parameter that was missing was the total cohesion. And here, Sylvain took remote sensing data to get an estimate of the vegetation distribution, because if we know the vegetation, we can estimate what the root cohesion is. And he then included all this information into a Monte Carlo simulation, which then resulted in a landslide probability map that is shown here, which shows us that we have, you know, high landslide probability in this area of the Berkeley Lab campus, which is also where our office is. Then in this area, where especially in winter, almost every year we have some landslides. They're very shallow, but they're almost every year there are landslides here. And then we had high landslide probability up here, which when we walked there and had a look at it, we also found a lot of signs of slope deformation. So the map that we got made a lot of sense. But then we focused on one site, which is right next to our office. But more importantly, it's a landslide that affects this bridge that I already mentioned that is monitored using a ruler, as you can see here. But this bridge is actually pretty critical to the emergency response of the Berkeley Hills. And because the landslide has deformed it quite a bit already, they're actually currently rebuilding it. So here we tested whether we can use ambient seismic noise as a tool to better understand landslide dynamics. So Sylvain put out some of these 3-component geophones, and we monitored this landslide for quite a while. In October last year, we had a pretty intense rainfall event where in just a couple of weeks or so, we had almost 200 millimeters of rain. And this was then a good opportunity to test this approach, right? So what we show here is some of the data that we got. And basically what is shown here is the correlation coefficient of an autocorrelation of the seismic signals, which shows us, in case the correlation coefficient is high, is basically that, you know, the seismic signals are not changing, which means that the subsurface is not changing. Now, what we found is that as soon as it starts raining, we lose this correlation coefficient, particularly in the higher frequency bands, which shows us that, you know, in the very shallow subsurface, which is responsible for the high frequency response, we see some changes, which are mostly related to, you know, infiltration, for instance. And then shortly after that, or after a while, after a few hours, especially in this area here, we get this complete loss of the correlation throughout almost all frequency bands. And this means just that the subsurface down to a certain depth is changing quite significantly. And what's interesting here is then that, you know, 5 hours after we see this loss, we actually start seeing movements of the landslide. And very similarly at a different station, so this is the station at the bottom of the landslide. Here we have one that's at the top of it. We see a similar response, so we lose the correlation coefficient, and then just 3 hours later, again, we see an increase in movements. So this shows us that, you know, we can use this ambient seismic noise, or we can use signals from ambient seismic noise as landslide early warning. And this is something that has been shown already since some years. But what we can also see is that these relatively simple measurements we can use to get a better understanding of the landslide dynamics. So in this case, we now know that, you know, the lower part moves first, releases stresses, and then the upper part of the landslide moves. We also looked at the use of electrical resistivity tomography. And here we used ERT monitoring to extract the grounder table at this site, and then feed this information into a very simple geomechanical model to estimate the factor of safety of the slope. And the factor of safety just describes the ratio between the driving and restraining forces. So the closer you're to 1, the more unstable a slope is. And if it's below 1, it means that it's actively failing. So what we saw here is that increasing grounder table, and we see this here, increasing grounder table from the solid to the dashed line causes a decrease in the factor of safety. And here, in this case, we extracted it manually, but we also worked on supervised and unsupervised clustering to extract the grounder table automatically from the wealth of ERT monitoring data that we have at this site. And we can then use this to feed this into this model and you know, use it for near real-time estimation of the factor of safety of this site. But this was just focused on a single site. So how do we monitor the entire Berkeley Lab campus? And this then becomes a little more difficult, especially if you think, you know, you want to put ERT monitoring lines all across the lab. This clearly doesn't work. So what we did is we deployed a pretty dense wireless sensor network where we have 18 stations where we're measuring soil moisture and suction, which is shown here in green, at 3 different depths, so 10 centimeters, 30 centimeters, and 50 centimeters. And then we also installed, at 60 locations, we installed deformation sensors that we developed at Berkeley Lab. And as you can see from this map, we focused on the areas that we knew had high landslide probability. So here in the eastern part of the lab, and then central and northwestern part. And so as I just said, we installed 60 deformation sensors, and these deformation sensors are pretty neat. So I thought I'd provide a little more detail on them. So what we did here is we basically developed let's say an add-on to some temperature sensors that Baptiste had been working on, or is working on for some time now. So here what we have is basically a temperature sensor and an accelerometer sensor every 10 centimeters, and they're alternating. So every 10 centimeters we measure temperature, and every 10 centimeters we have a 3-component accelerometer that measures the deformation of this probe. So using the accelerometer, we are actually able to, you know, recover the shape of this probe at any given time. And we can do this with an accuracy of about 2 millimeters per meter. The probe itself and the logger, they run off 2 AA batteries. And if you don't transmit any data, you can actually log data for about 3 years at 5-minute sampling interval. And now if you turn on the data transmission, which is kind of crucial to a wireless sensor network, the battery life reduces, but you still have a battery life of about 1.5 years. So that's pretty neat. Down on the right here, we see an example of some data that we acquired in the Arctic. So that's not in Berkeley, but this shows you that also having a temperature measurement is very, very useful, because what we see here is that the ground is unfrozen on the top and then frozen at the bottom. Now, what we would expect is that we would get no movement where the ground is frozen, and we would get the movement in the unfrozen part. And that's exactly what we found with this probe. So in the frozen part, there's no movement. And as soon as we go in the unfrozen part, that's where we see movements, in this case, up to about 1 centimeter or so in just 5 days. So as I said, everything, the soil deformation probes, the soil moisture probes, they're all connected through LoRa to, in this case, 2 base stations that we have at the lab. And from these base stations, the data is then pushed to a database, and the data is then visualized in Grafana, which is an open source, dashboard style visualization that is shown here. And from that, we can have a good eye on what our sensors are doing, and where we have potentially high pore pressures, so where landslide risk or landslide hazard is increasing. And just to show you one more time that increasing soil moisture indeed causes slope instabilities, here's an example of the data we acquired of this network. So it's just one of those just water potential sensors that shows a rise in water potential just following a rainfall event. And we see pretty nicely that this then relates to displacements of about 1 centimeter again in this case. So very small movements, but we can recover them. And more recently, we're working on machine learning algorithms, and in particular long short-term memory models, to predict how soil moisture may change in the future. And we do this for 2 reasons. The first is we want to use this to make the sensor network adaptive, which means we would like to reduce the amount of data and battery consumption to measure a low sampling rate when not much is happening, and at high sampling rate if things are going to change. And second, if we can reliably predict into the future, we could also use this for early warning clearly. So we worked on 2 approaches here. One is basically training on 24 hours and predicting 1 hour, and the other one is training on 14 days and predicting 12 hours. Now, if we predict just 1 hour ahead, our results are pretty good. And that's something that we can use for adaptive sensing strategies, for instance. If we try to predict 12 hours ahead, we are pretty good in predicting gradational changes. So here you can see that the error is pretty small, but we really fail in predicting more sudden changes. And this is mainly because of a lack of training data. So in this case, we only had 1 year of data, which was a very dry winter. And so we only had 3 or 4 storm events we could train on. And this is clearly not enough to basically predict the response of such a storm event. So what I was hoping to show you is just an approach that we're working on that really integrates various sensing techniques, so near surface geophysics, environmental monitoring, integrating it with hydrogeomechanical modeling to assess slope stability in real time and to predict at some point into the future. And with this, I think we're able to provide a predictive understanding of slope instabilities that will help us in providing reliable and robust early warning. But of course, this is still a work in progress. And actually, we were in a way pretty lucky at the lab now, because the lab management, realized that we're doing this, and they're actually now trying to extend this monitoring network and really making it part of their site operations to reduce the landslide hazard at this site. So this is something that's pretty nice and encouraging, because you can actually see an application of the work that you're doing. So is this a step closer towards predictive understanding? Is near surface geophysics actually a useful tool for landslide hazard assessment? And in this case, it really is a yes. And if you look at recent literature, you will see a lot of applications where near surface geophysics is used almost as standard in landslide hazard assessment. And there are also international networks of landslide early warning systems that really understand that near surface geophysics is a valuable tool for their early warning systems. So that's all I want to talk about. I want to finish with just a couple of pictures. So here's a picture of Sylvain putting in one of those deformation sensors, having a nice view of the Golden Gate Bridge that's just in the back here. This is just to show you that we indeed have pretty steep slopes at Berkeley Lab. And then on the back here, we have a picture of the Arctic at a site where we installed these probes as well, where now we are starting to monitor, how permafrost thaw is, causing or triggering slope displacements, and having this kind of information, but also geophysics is really helpful in understanding these processes that are not particularly well understood yet. So with this, yeah, I'm very happy to take any questions you may have. And thank you very much again for giving me the opportunity to present this work today. So thank you very much.
Yeah, thank you, Sebastian. Pause. I put a note in the chat. Please feel free to ask questions of Sebastian in the chat or raise your hand and ask yourself. I don't see any yet, so I'll ask one while we're waiting for hands. I thought the accelerometers were really interesting as an additional data type. Are there other types of data that you think you could integrate in low-cost sensors that would help to reduce uncertainty in these near-time, real-time predictions that you're all thinking about?
It's not probably, well, you're getting more into low cost too, but we saw that, or what I showed too is, that ambient seismic noise can be a very good predictor of things that may happen related to landslides. And at least at the lab, there's maybe an opportunity to put more of those out. But the problem then is, you're acquiring a lot of data, and how do you transmit the data? How do you store the data? And that's also what makes the devices more power hungry, so it will also then increase their cost. So making this low cost and having a pretty dense sensor network of kind of geophones would be something that would be really interesting. But I think this still needs a bit of work, especially in terms of building a logger and making sure that you can transmit and store the data kind of at low power.
Well, thanks. I see Jonathan has his hand up.
Really cool stuff, Seb. I really enjoyed that talk. I did have a couple little questions on the sensor telemetry and the long distance radio and everything, because that's amazing battery life with any type of transmission. So I was wondering if you could elaborate a little more on the hardware you need to keep these very persistent autonomous sensors going. I'm also really, go back to the slide you just skipped over, the one which showed the transmission. Yeah, and so I was curious about also, whether or not this is a pretty easy to port kind of framework for the sensor web stuff, because that's not provided by Grafana, right? So you must have, put together the database and everything on the back end, because this seems like it's something which is really generally useful for any time people want to do autonomous measurements, for a long time.
So to your first question, so at the lab we have Stan Wieland, who is an electrical engineer, and he developed all of the hardware, right? So he made sure that he uses the right components to make it, with as little power consumption as possible. And he tweaked it so that it really has very little power consumption. So of course, if you would just start building it based on, I don't know, a Raspberry Pi or an Arduino, you wouldn't get there. But he really built all the hardware to actually enable this very low power consumption. And he also worked on, for instance, data compression algorithms that minimize the time that you need to transmit data. And if you minimize the time that you need to transmit data, that's mainly how you save energy, right? And he could actually show that by using his compression technique, he could increase the battery life by a factor of 3 or 5 even, but I think it was 3. So, even just data compression really helps to increase battery life. Now, for this is all based on open source codes. So, InfluxDB is a database that's pretty easily accessible and to set up. Grafana is all open source, and you can set it up pretty easily. And I mean, I don't have that much background, but I was also able to just write a bit of Python code that feeds my data into the InfluxDB database. So there is a lot out there that actually helps you to now push all the data into a database and have it accessible relatively easily. And you don't need to use Grafana. I mean, once you have a database with all your data, it's very easy to just write a bit of code that pulls the data and maybe even puts it on a public data on a public website, which is something that I'm currently working on. So yeah, it's pretty easy. I mean, as always, it's a steep learning curve, but it's kind of easy. So.
Are there any other questions out there? Got about 8 minutes to the end of the hour. While you're thinking of one more question, I put in the chat some reminders. Sign up to be an OSPA judge. Sebastian will be handing you about that as our OSPA coordinator. Come in person on Tuesday evening for the in-person version of this section meeting. Join us Thursday at Kroll's. And remember to congratulate our awardees when you see them in person at AGU. I see a question from Kian. I'll read. Your real-time monitoring dashboard looked quite valuable. Is that just for IoT sensors with direct measurements, or are you doing automated real-time processing? Curious if you see this as an option for displaying edge process data or locally cloud process data of geophysical monitoring that requires processing. A lot there, so feel free to chime in on that.
Yeah, so for now, this is only the data from the IoT sensors. So I think, I mean, what you're saying is yeah, I mean, that's certainly, I mean, if you could put, you know, edge process data or cloud process data into it as well, that would be great. I mean, you could do it, you know, already now we do some processing of the accelerometer data in the cloud basically and push this to it too. But for the geophysical monitoring data, no, we haven't put this in yet. But yeah, this would be certainly something that would be really awesome to do. But for instance, people at the BGS, at the British Geological Survey, I think they have a, I mean, they have a, is a commercial software, but I think they're working together with people that actually put the processed geophysical data onto a dashboard like this as well. It's just not freely available.
Thanks. Any other questions out there? Okay, well, thanks everybody again for joining. Congratulations to everybody who was recognized this year, and I hope to see you in just a week's time. Thanks, everyone.